gente começa já? Ok, então, okay, we are going to speak in English now. Hello, welcome to the 7th class of this basic course on stochastic programming. I am Juan Pablo Luna, and I am going to give the next 3 classes of this course. Okay, first, one announce. Tonight actually, we are going to release the first list for the course. So I'm not sure how many questions it's going to have, maybe 6 questions or a little more. You will have to choose between them 4 questions. You need to resolve that, and you will need to send via email or to give us in paper here before the class on the next Tuesday. Okay. In the site, in the website of the course, we are going to release this list today at night, and further instructions about that. Okay, that's the only announcement, and so we are going to start the class. Okay. Today we are going to speak about the interchangeability property. This property is related to the equivalence between those 2 formulations that we have already. We have here, for example, the 2-stage problems. This 2-stage problem is written in a more general way. Okay. As you can see, this is not a linear problem as we have seen in the previous lectures, but it's quite similar. For example, for the case of the linear problems, this is going to be something like this. G of y x c is going to be only this. Maybe this is depending on the random vector. This set, okay, this is a little different. This is a multi-valued function. Okay, to each of these 2 values, we have associated a set. For the case of the linear problems, this was something like this. Maybe this depends also on the random vector y and 0. Okay, so as you can see, using these values, we have the linear problems we were working on the previous lessons. Okay, here we have a crucial point. In order to evaluate this expected value, we need this function q to be measurable. Otherwise, it doesn't make sense to try to have this expected value. Okay. So, but as you can see here, the definition of this function is the optimal value of an optimization problem. So you cannot expect this function to have very special properties because it's an optimal value of an optimization problem. So the properties of this function is related to the properties of these components of the optimization problem we are using to define it. Okay, so if these functions are not well behaved, maybe this function is not measurable. And so today we are going to see some cases in which we can ensure that that function is measurable. Okay, the easy case in this for this is when the random vector c is a discrete random vector, then you will have that actually this will be a discrete random variable. Okay, and so in that's this case. So, I mean, no matter which properties this components has, if the discrete random vector is, if the random vector is discrete, then this will be a discrete random variable, and it will be measurable, of course. Okay, but in the general case, maybe that's not the case. And as you can see here, we have an example. We are considering the probability space as being these segments 0, 1, okay, with the Oliveira measure. So we can take this random vector as being actually a random variable. We can define this feasible set as the segment 0, 1. So it's quite regular, okay, it's fixed. But the objective function is a little more complex. Okay, I am going to write that here. This is something like this is function here y minus who is that? I think it's better to put my, oh, it's a little different. No, this is square, isn't it? Okay, it's like that, like this. When you know that this function sine is defined in this way. 1 if z is greater than 0, 0 if z is equal to 0, minus 1 if z is less than 0. Okay. As I have said, this n 0, 1 is non measurable set. Okay. Well, I don't know if you are acquainted to this fact, but in this set, for example, it's in measurable theory courses, you can show that there exists actually some sets that are not Oliveira measurable. Okay, so we are taking one set like this, and we are defining this this function that is we can take well, we can take 1 if z belongs to and 0. Yeah, I think there's a, oh yeah, I was forgetting this. Okay, so as you can see, for fixed value of y, you have that is measurable. Okay, because when you fix y, all this expression is fixed, and you only have this random variable that can be that is a random variable, so it's affected to n square, so there's no problem. It's continuing being a random variable applied with this function. It's a random variable. Okay, so but if we solve this problem, Q is minimization of this. It's going to be square that. Okay. this is going to be okay. If y belongs to this set, okay, if y belongs to this set, this quantity is going to be equal to 1 all the time, okay? For y belonging to, if y belongs to that set. No, wait. No, I want to do it in another way. What happens if we have something like this?
Sorry, the sine function applied to the square, won't it always get like positive like numbers?
Not because, okay, this is a square, but if this value here inside is different from 0, okay, a square is going to be positive, and you will have 1. Right. But if this is 0, you will have 0. So that's the point. Okay. Okay. So let's see this. What is the solution of this problem? Okay. Oh, okay. If this value does not belong to this set, okay, then this point is going to be different from 0, isn't it? It's going to be different from 0 because this value is always 0 or a value that is in this set. Okay, so if this doesn't belong to this set, this is different from 0, this is going to be 1. And if this value belongs to this set, well, at some point, these two values are going to be equal, and then this is going to be 0, and you will have a 0 because you are minimizing. Okay? So, well, as you can see, this is not a random variable because if you take the inverse image of, I don't know, 0, for example, it should be measurable, but the set n is not measurable. Okay?
Why is equal to, is it just the example or?
Sorry?
I don't understand why why it's equal to this expression. It's just
This one?
yes.
Why I choose that expression?
Yes.
It's an example because what we are trying to show is an example where you have an optimization problem that is defined in this second stage function, and this second stage function, as we show it right just now, is not measurable. So you cannot have it doesn't make sense to try to take this expected value. Okay, so that shows that you need to choose these two elements in such a way that this should be measurable. So there are cases when this will not be measurable and you cannot take the expected value and it's not working. Okay, so the class today is we will be which properties we need to ensure on these components to ensure that this is going to be measurable. That's the point. And this is an example where you don't have that. Okay? Let's continue. Okay, this is the one stage problem that we can construct related to this other one. Okay? As you can see, these first stage constraints and these other second stage constraints are together in a unique problem, and the the objective function are related to this one. So I mean, this is the same one, but instead of taking this second stage function, we are using this one. Okay, Claudia in the previous lessons has used the property that these two problems were equivalent. Okay, so the objective now is to show that they are actually equivalent. But for defining this other, for defining this other problem, we need to ensure that actually this random variable is actually that this is a random variable. I mean that this is actually a measurable function. If not, you cannot take that expected value. And look that this vector yc is being chosen in this set, but you are not asking any additional property. Okay, since you are not asking for any additional property to this value, you cannot expect that this function is going to be measurable. So perhaps it doesn't make sense to have that expected value. Okay. Well, on the other hand, well, you can ask to this variable to be measurable. For example, instead of choosing arbitrarily values here, you can try to choose in such a way that together all of them defines a random vector. Okay, so in that case, after some regularity conditions on this function, you can expect that this is going to be a random variable. It's an option, but in general, for defining this, you don't need this vector yc to be random. You only need this function to be measurable. Okay. I think there's some problem on this.
So for each yc fixed, g yx is
For this fixed?
yeah, the function g.
Oh, this g. Okay.
Is that what you are implying?
Sorry, can you repeat that? For it
Fix the y variable.
y.
Yes.
Okay, you are fixing y.
This function is measurable with respect to c. Is what you implying?
Yeah, that's something that you will ask. That once you fix this value, this is going to be measurable. Okay, but for using this, you are not fixing y, because y is changing with c. So now you are changing this value with the values of c. So maybe now this is not measurable. For each value fixed here is measurable, of course, but now you are changing all the time this one. So maybe this is not measurable. Okay. I think
The y of c depends on x, or
yeah, because you are yeah, it depends on x as well. That's true. As in the previous case. In this other previous case, okay, it seems that something on my files were not synchronized, so this file I think is not the right one, but there is another comment that I should have made at this point. For example, even if you can ensure that this is measurable, for example, you know that for this fixed x and y, you have a minimizer here, okay? That is going to be something like y x c, for example. Okay, so as a function of c, you have a function on the random vector, okay? And you can ask, is this measurable as well? Maybe not, because it's not connected. You are fixing all these values here, and you are choosing a minimizer, and this is not connected with other different values of this. So there is no reason to have any special property this function. It doesn't have to be continuous or measurable. Okay? But as we will see later, there will be measurable depending on some conditions on these two components. That is the objective of these lessons. Okay. Now, oh, okay. But of course, if the random vector C is discrete, there's no problem. Everything is discrete, and you don't need to worry about these things. Okay, and in practice, when you are solving the optimization problem, you are using a discrete variable. Because the problem is discrete actually, or maybe because you are using a discrete approximation of a continuous random variable. So for that side, there will be no problem. But for theoretical reasons, it can appear some problems. Okay. Well, here we have a proposition. It means that assuming that these functions are always measurable, and so you can assume that, and that this is always measurable, and that the minimizers of both problems are always measurable, assuming that is quite a strong assumption, then the one-stage and two-stage problems are equivalent, in fact. So even for the, how to say that, for the discrete case, they are completely equivalent. Okay. For the general case, there will be equivalent as long as you can ensure that these three quantities are measurable. And the proof is easy. Yeah, I can do the proof. The first stage problem, the two-stage problem is defined like this: f of x plus the expected value of q. X belonging to something like this, and you have that over y g yc subject to y belonging to. Okay. Assume that this is always measurable and the solution are as well measurable, and then assume that x bar is a minimizer. This is a minimizer, and this one as well is a. I can write in this way. X bar is the minimizer. Of the second stage problem. Okay, we have the x bar a minimizer of this problem, and we have the minimizers for that fixed x bar here. We have the y bar that is a minimizer of this other problem. What we want to show is that actually these two are going to be the minimizers of the one-stage problem. Okay, and that is going to be easy, I think. Okay, given x, y, c, feasible point. Feasible point for this other problem. Okay. Oh, here is it. Oh, why? Okay, so I am having a feasible point for this problem. What we want to prove is that this pair is actually feasible to this problem as well, and the objective function on these two values is less than the objective function evaluated on these two values. Well, okay, x bar, since x bar is the solution of this problem, x bar belongs to capital X, so it's feasible for this, okay? On the other hand, since this is a minimizer for this other problem, you know that this value belongs to this set when you fix x bar here, okay? So you can see that we can see that this is feasible for the one stage problem. Okay. On the other hand, let me see. On the other hand, we have that. G of x, this is greater or equal than this here, okay? Because this is the optimal value to this problem. Okay, we have that. Then since we have that, we have, of course, this other value. Okay, and actually we can have this. Because I am adding only one constant, okay? So there's no problem. But since x bar is a minimizer for this problem, we have that all this is greater or equal than okay. And finally, oh, always happens this. Finally, noting that that this thing here is this one. Okay, we have so as you can see, this pair is a solution for this stage problem, this one stage problem. So this ends the first part of the proof. The other part is quite similar, so I am not going to do that. Okay, now I am sure this file is not the right one. Something in the Dropbox didn't work as I expected, but it is good enough for continuing giving the lesson. Okay, so the functions we are interested to work with are the so-called category functions. Okay, these functions are defined on this in this product set. Okay, here usually you're going to have in a more general setting a probability space. So you need that for any first variable fixed, this should be measurable. That is quite natural to ask it. And for any this second value, this function needs to be continuous almost everywhere. With those two conditions, we will have a family of functions that will be well behaved for our applications. There are more general functions that will work as well, but I think these category functions are good enough for all the things we are going to work. Actually, in practice, you will have that this will be not only continuous but differentiable. So continuity is good enough. Okay. Oh my God, this file is not good. Let me see. Thing here. No. Oh. Okay. The first thing we want to speak about is that okay, we can have a proposition here. Position. No. Let's take some notes, okay? Some remarks. Consider f that is going to be Rn times some probability space, category function. Let me speak the category function. Then we will have we can define this other function here. Okay, we are defining this function as the optimal value of an optimization problem. As you can see now, of course, this function here doesn't need to be measurable in principle. What we want to prove is that if this function is a category function, then this is going to be measurable no matter which set is this set S. Okay? And only to see how this works, let's start with some simple cases. If S is finite, let's say that's x1, x2, xn. Okay, if this set were finite, then actually what we have is that this function will be the minimum of f of xi c. Let me put n. Okay, and of course this is going to be a measurable function. Do you agree with that? Because I am having only now I know that for each fixed xi, you have that this is going to be measurable. Okay, and you have a finite quantity of those functions. You are minimizing. You're taking the minimum of all these functions. This is going to be measurable. Do you agree? Okay, the minimum of measurable function is measurable function. Actually, if you have here that an countable quantity, 1, 2, it's going to be still. I mean, this will be still a measurable function because the minimum of a countable number of measurable function is measurable function. Okay. The other case is when you have S that is some set of Rn, maybe non-countable. In that case, it's a little more complicated. And look that at this point, we only use the property that for each fixed xi, this was a measurable function. I was not using the properties, the special properties of a category function. At this point, we need to use that. Okay. And how we can do that? Okay. Okay, what we are going to do at this point is take S hat equal to S1, S2, subset of S, such that that is dense. This is possible to do. You always can choose a subset of any set S that is dense on that subset. Then we can define this other function. Define, let's say, this function here, that is the infimum of a okay. Okay. We are using now we are defining this other function using only the elements of this other function that is dense on S. Okay, so this function is measurable. Okay, this function is measurable, and the objective now is to prove that actually this function and this other one, sorry, here we need an infimum, are the same. Okay, so how we can prove that? It's clear. Okay, it's clear that okay, because this infimum was taken over a subset of S. On the other hand, we can take a sequence, for a fixed C, a sequence let's call it something like E, okay, such that the limit of okay, we can do that because this function is the infimum of this function evaluated of all values of x that are in S. Oh, this is in S, such that that happens. And now let me think what we can do at this point. Okay, and since is dense in S bar, we have that. We have that for each I in the set of natural numbers there exists. Oh, let's put here J. There exists is ij in this set such that here's something like this. No, doesn't have this. Okay. Minus x less than 1 and 1j. We can have that because the set is dense. Okay, so with that, that's enough to prove that. Okay, with this, we know that these two sequences are the differences converging to 0. I am not sure if that's enough to prove that then these values are going to convert to this value actually. It's going. Yeah, I am trying to use that continuity, but I am not sure now. Yeah, the problem is maybe this doesn't have a limit. That's the problem. The difference is going to be 0, but each sequence, I don't know if the sequences are going to be. Yeah, what I want to compare is this and this. Okay, but if we have a compact set, it's going to be easy. But the set S is not compact. Yeah, that's the problem. The set S is not compact. I am not sure if we can take some bounded set of S. Let me think about that. Okay, let's put. No, I think there's another way to do this. Let me think about this. Let me think about this. Yeah, I think that we can do in another way this. I was thinking to do in this direction, but we can do in another way, okay? For any epsilon greater than 0, okay? By continuity, of this function here, okay, there exists let's say delta I, okay, greater than 0, such that f of x is less or equal than f of x I c, as long as for all Okay, just continuity. For each xi, I have a value delta I, such that for any point that is close enough to xi, you can have this. Oh, sorry. Okay, and since this set is contained here is dense, there exists as let's say ji such that actually this happens. Okay, and so we have that this happens. Oh, sorry, I was forgetting this here, here, and here. Okay. Here, here. Okay. And of course, this is greater or equal than this point. Okay. Oh, and okay. So using this this equation, taking the limit when I goes to plus infinity, we have that. Okay, taking this limit here, we have that is less or equal than this plus epsilon for any epsilon greater than 0. This implies and so is measurable. Okay. Ooh. I thought that it wasn't going to work, but worked. So as you can see, if we define a function like this, for any set S in Rn, as long as this is a characteristic function, you can ensure that this is measurable. Okay, so it's a good function, but our problem is a little different because we do not have something like that. We are here this feasible set that is changing with the scenarios. Okay, we were using only a fixed set, so ensuring that this is going to be ensuring that this is a measurable function is not that easy. But at least we know that we are using the right tools. And actually, we have this theorem here that says that as long as this function g is a characteristic function, and this on all components of this function here are as well characteristic functions, we can ensure that this is going to be a measurable function. Okay, but for that we need another result that is going to appear in the file we will release at night, but that didn't appear here. It's this proposition. Proposition. Let's say. Let's see. That goes from times omega to Rm. Okay. Via function. Function whose all components ci, okay, I mean c is equal to c1, c2, cm. All components ci are carottedori functions. Then functions. Okay. Okay. For a function like this, there exists a family how am I going to GI a countable family of measurable functions such that this set is contained here. Is dense. Okay. So as you can see, this is going to be a feasible set. Okay, and for every fixed scenario C, you have that. After fixing this scenario on this family of functions, you will have a numerable quantity of points. This subset is going to be dense. Okay, so you have something like this. Let me try to let me try to give a graphic idea. Maybe you have something like this here. This set is going to be y c1 less or equal than 0. And if you change this scenario, maybe you are going to have a different thing here, which is cy 0. And if you change another time the scenario, the feasible set is changing along the scenarios, okay? But that this theorem says is that there exists a countable family of measurable functions such that all of them are contained on this feasible set. So there is something. It's something like this. This should be G. So here is G C1, and it's going to pass here. C2 is going to pass here. C3. You know already that this is measurable. In the same way, here you have another G1. Let's say that. Oh, G1, G1, G1. Here you have another one, G2, and you have here a point, G2 in C1. Let me take a bigger triangle here. Here you have from G2, C2, you have G2, C3. And you have a family of those functions, G3, a countable quantity of functions that are already measurable. And you know that all these points here are dense. Here, all those points are dense, and so in this point, okay? So that is the interest. That is what is interesting in this proposition, because even if the feasible sets are changing, you have a family of functions that are dense enough here, that dense enough to be representative on these feasible sets, and are countable. So with using that property that to be countable, we can ensure that this function is going to be measurable. Okay, so for proving this theorem, I am not going to prove that, but I am going to do the route for doing that. For example, we can define this other function, okay, which will be the infimum of G okay. So as you can see, instead of using the whole feasible set, I am using only these functions. Okay, so I have a countable number of functions here. So if these functions were measurable, this is going to be measurable. Okay, but for that we need to use another proposition. If G is a caretatory function, then G is measurable on let me on R N is this RM this. Okay, so because if this function g is a category function, we know that fixing y, this is going to be measurable. If you fix xc, this is going to be continuous. But doesn't that doesn't mean that this function is going to be measurable in this product space. Okay, but this proposition ensures that this is going to be actually measurable in this product space. Okay, so since that is measurable in this that product space, and since these functions are all measurable, you can ensure that this function is measurable. Okay, so that's since that function is measurable, you can you have that this q hat is measurable as well, and you will have that q. This is going to be less or equal than this. Okay, we are almost there, and since these values are dense on the feasible set, you will have, again, by continuity of g, you will have that these two will be equal. So that's enough to prove that this is measurable function. Okay, so you can see that all we need are category functions. And for example, for the linear case, we have that g of yc is going to be qc y. Okay, and that's a category function, obviously, because every time you fix this y, this vector is depending on this c vector, and you can ask it to be measurable. That's a quite natural hypothesis. And if you fix this this c vector, obviously this is continuous, so there's no problem. And for the feasible set, such that something like this. Again, you can write this. You can write a function like C1, for example. We can define like as being this. Okay. Oh, yc. Okay, and we can take this C1 minus C1. Okay, then then we have this. y such that c and 0. Okay, and you can see that this is a Cartesian function as well, because all these elements are measurable. So if you fix x and y, this function is going to be measurable. And if you fix the random vector c, this is going to be continuous. So this feasible set for the linear case is good enough to ensure that this function will be measurable. Okay. There's another theorem that should appear on the slides but didn't appear. Is this one. This theorem is called the interchangeability theorem. Okay, and that's the important one. Let's say that is given g of y c and c of y c, okay, Cartesian functions, and this function here defined as the optimal value of this function here. Okay, we already know that this is going to be measurable. Okay, because all these are Cartesian functions. Okay, with these assumptions, we will have that. Okay. Here?
Yes, because
Why not?
your C does not depend on X.
Oh, no, but x is fixed. X is fixed. So there's no problem. Here you can plug 0. There's no difference. Because for a fixed, what you fix x, and then you have a function that depends on c. And you need that to be a measurable function. Okay, so for that you fix this here. You need these other components that doesn't depend on x. That if you need them to be Cartesian functions, and you can ensure that this function is going to be a measurable function. So it doesn't depend on x. So here you fix this. This is another parameter, and there's no problem.
You may think of the composition of Q with H minus G of X.
Okay, yeah. Well, actually, if you try to put in this form, you should use something like CYC, something like this. Okay, and oh no, you need to do this. No, this should be something like this. Minus okay, x is fixed. So this function is going to depend only on y and c. Okay, x is fixed, and if you fix y, obviously this is measurable because this is measurable, all of this is measurable. If you fix xi, okay, so this is continuous. So it's a Cartesian function. Okay, so what was I saying about this theorem? Okay, send this. If okay, you know already that this is a measurable function. Okay, so if you have that the expected value of this measurable function is a real number, okay? I mean, it's not plus infinite nor minus infinite, then you can ensure that then you can ensure that this expected value is going to be the infimum of these expected values here. Such that zero and is measurable. No, actually, we need to put something like this. On some set. Okay. Also, is the minimizer of let's say this okay. So what is saying this this theorem is that well, we know already that this is measurable, and if the expected value is a number, is a real number, then this expected value can be computed as this optimization problem. Where for each scenario, see you are looking for a y that is depending on that scenario, and this vector should be measurable. Actually, should be in some special space like LP. Okay, and this if you have a minimizer for this problem, you already know that this is going to be measurable, and you have also that these values are the minimizers of these problems. Okay, so what it's saying is that if you solve this problem for each xc, you will have a yxc, that is the minimizer. Okay, they are, as I have said at the beginning of this lesson, they are not connected, but that theorem is saying that actually they will be measurable random functions. Okay. Okay, so what it says is, if we come back here, for example, what it says is, if we solve this problem, okay, for an x bar, for example, and you fix that x bar here, and you solve this second stage problem, you will have a y that depends on that x bar fixed and that c. Okay, so here you will have a function y x c. That's a minimizer. Then what it's saying is, as a function of c, this is measurable. Okay. And the other thing is, what it's saying is that actually these two problems will be equivalent. As a remark to the, oh, sorry, these slides are not updated. Not this one. Okay. As a remark, we have the following. For the linear problem, no, I'm going to put in a different way. I don't know, I can't remember which letter Claudia uses here, but I'm going to do in a similar way. Okay, this is the linear problem, the second stage linear problem we were using on the previous lessons. The dual problem. The dual problem is, what's the dual problem? Maximize pi transpose I'm not sure this is going to be the dual problem. Okay. We can put this in this way so that we can minimize this problem. Okay. Okay. And this is, I'm going to put, I don't know, maybe d of cn, no, ox. Okay, we have this dual problem, and as you can see, the decision variable is pi here, and as a decision variable of pi, this is character. Category function. Okay, and obviously this one is as well a category function. Okay, so this is going to be a measurable function and everything like that, and usually this is going to be a finite over, well, if the primal problem is finite. I mean, if we are in the regular cases, okay, this is going to be finite. Then the Lagrangian then we will obtain the Lagrangian multipliers Lagrangian multipliers that will depend on the random vectors. Okay, so Lagrangian multipliers are solutions of the Bell problem. Okay. By the theorem is measurable. Okay. So as an application of that, we can be sure now that the Lagrangian multipliers will be measured as well. So it makes sense to take the expected value and everything that we were doing in the previous lessons. So I think that is all for today. Do you have any questions or comments or something like that? If not, we will meet again on Thursday. Okay? So see you then.